Hello everyone, welcome back to PHYMICS, where physics and math meets imagination. In this series, we will be diving into something that looks simple, but holds the power to shape curves, predict motion, and even land rockets: quadratic polynomials. By the end of this series, you will not only understand what a quadratic polynomial is, but also see how it's used in the real world. And trust me, it's cooler than you think. So grab your notebook, hit the like button, and let's explore the magic of x square right here on PHYMICS. Imagine you are building a roller coaster. The track curves up, then dips down, a perfect smooth arc. Or think of the path of the basketball flying through the air. These curves are not random. They follow a special rule, described by something called quadratic polynomial. So what a quadratic polynomial exactly? And how can something as simple as x square be behind so many things around us? Let's break it down step by step. A quadratic polynomial is an algebraic expression of the form ax squared plus bx plus c where a is not equal to 0. So what does ax squared plus bx plus c mean? Let's further break it down. A is the coefficient of x squared and it controls how wide or narrow the curve is. B is the coefficient of x and it affects the slope or tilt of the curve. C is the constant and it tells where the curve cuts the y-axis. Put it all together and you got a quadratic polynomial, an expression of degree 2. Graph it and what do you get? A beautiful curve called parabola, either opening up like a smile or down like a frown, depending on the sign of A. The parabolic curve always cuts the y-axis at coordinate 0, c. The most important point on the parabola is the vertex, the turning point. It's where the parabola reaches its minimum or maximum values. A parabola is perfectly symmetrical about a vertical line called the axis of symmetry which passes through the vertex. Zeros of the polynomial are the values of x where ax squared plus bx plus c becomes 0. In the graph, these are the points where the parabola touches the x-axis. Depending on the graph, we have two distinct routes depending on where the parabola cuts the x-axis at two different points. One repeated 0, the parabola just touches the x-axis at the vertex. No real zeros, the parabola that never meets the x-axis. And that's the magic of quadratic parabola, a single expression with world of information. Now one more question arises, why we need to calculate the zeros of the polynomial? Zeros of the polynomial are more than just maths answer. In graphs, these are the intersection points. In physics, these are the critical events. And in commerce, they are the decision-making thresholds. In the next video, we will be deriving the standard results for the vertex and the relationship between zeros and the coefficients. So stay tuned. Thank you for watching.